All right, so this is CISSP. And as the student pointed out, if you're in the 127 class, there is a lecture tomorrow. There was going to be a tech talk, but it's on Thursday instead. So have a normal lecture tomorrow in the 127 class. And tonight we'll cover the first bit of Chapter 4, which is Network Plus is what it is. Same thing covered in the classic networking information that you'd get in a first Cisco class or in this CompTIA class covering Network Plus. So as soon as my slides pop up, there we go. That should be it. Yes. There we go. All right. So, network design, fundamental concepts of networking. Simplex is one-way communication, where you talk in one direction. For example, broadcast TV. You just send out a message, there's no way to reply. Half duplex is where you can send or receive, but one at a time. So this is walkie-talkies where I say something and then over, and then you can talk and you say over, and then I can talk. We have to take turns talking. We can't both talk at the same time. That's full duplex, which is what most people want. That's like real life, where it's two-way transmission and multiple people can talk at the same time. The mechanism supports that. Then you can decide how much of the frequency range available in your network communication hardware is going to be dedicated to one channel. Baseband is most common in computer networking, where you have an Ethernet cable and you're allowed to use all the frequencies in that cable for one computer going to one device. But on things like AM and FM radio, you have broadband, where there are multiple channels and each get only a portion of the available bandwidth. Analog signals are the older technology, where you just have a continuously varying signal, like an analog signal going into a speaker, and the speaker just has a displacement of the moving part, the cone, proportional to the voltage, and so you get a replication of the signal coming in, but it is not precise, and every time you transmit it again, it degrades more and more and gets more and more noise. Digital is the modern technique, where instead of actually directly transmitting the pressure of the air, you digitize it and then send a signal of zeros and ones, and you can include checksums and hash values and such in that, so that any errors can be repaired. So you can send it over a network with 100% accuracy, and you can store it and make multiple copies of it with 100% accuracy. Then you got networks, the local area network within a building, and the wide area network covering cities, states, or countries, and these other ones less commonly talked about, like the personal area network, which are all the devices you might carry on your body with Bluetooth, and so on. So the Internet is the global network of networks running the TCP/IP protocol suite, which was originally designed for Unix and became the winner, and therefore became the standard networking used for all purposes. Intranet is a privately owned network using TCP/IP, and then there are extranets, where you let some limited portion of people outside your network in, like your suppliers, that you let come in with a VPN. Circuit switch networks are the kind where you have a wire completely dedicated to one channel for one connection. If you get a T1 line, that is a dedicated wire just for you, or a simulation of the same thing. A packet switch network is what most internet traffic and most LAN traffic also goes over, where multiple signals share the same line. You have many devices going into a router, and then one trunk line coming out of the router going to the internet, and that trunk line is carrying many different devices' traffic, one packet at a time, just strobing between them. This is much cheaper, but of course they're all sharing one total amount of bandwidth, and they can't exceed that. So the quality of service is a tag you can add to a packet to indicate that this is a high priority packet and other packets should wait for it. This is important for voice over IP. If you want your telephone calls to move over your data network, you must give your telephone calls higher priority than, say, the email and the web traffic, because humans can hear a small delay, like 10 or 50 milliseconds, and they don't notice 10 or 50 milliseconds in the time it takes to load a web page. So you want to label the voice over IP packets with a higher quality of service. So there are layers in the TCP/IP stack and in all networking. This is a technique so that you can make devices and make devices interact with other devices and software written by other people. It's just a way to specify, to split up the work into different pieces. So there's a network model. The most common one used is an OSI model, but the one that's really used in reality is the TCP/IP model. So the OSI model has 7 layers, and there are mnemonics here like please do not throw sausage pizza away. You have the physical layer, which carries the bits. You have the data link layer, which has MAC addresses. You have the network layer, which has IP addresses. The transport layer that has TCP and UDP ports. And the session layer that measures things like whether you have logged in to some kind of account or network share. Then a presentation layer that handles issues like compressing and encrypting data. And then the application layer, which finally presents something a human can understand to the end user, like a viewable image or a readable email. And so everything is done in these layers. So the physical layer has the protocol data unit of a bit, and this is the Ethernet cables or the radio or the fiber optic medium that carry the bits, and things like hubs and repeaters and cables are at layer 1. Layer 2 uses MAC addresses for Ethernet, the most common layer 2 protocol, and it moves chunks of data called frames, which have some kind of address in the front of them, followed by data, and that address is used to route them to the correct device, although you don't call it routing at this label, there you call it switching. And so switches, Ethernet cards, and bridges are at layer 2. Layer 3, layer 2 also has 2 sublayers, the media access control and the logical link control are the 2 sublayers of layer 2. And the network layer is where you have routing. You have a logical address called an IP address, which determines the physical location of your computer, so data can be sent over the earth and find you physically. Now, IPv4 and IPv6 are the protocols used here, and routers are in layer 3 that move data large distances to find the right physical location of the end device. Layer 4 is the transport layer, which is used to determine, once you have found the end device you're trying to talk to, this determines which process on that device you want to talk to. One device can serve multiple purposes by listening on different TCP or UDP ports. So in comes segments of data, including UDP and TCP port numbers. TCP is the most common protocol because, although it is slower and more complex than UDP, it is more reliable. You can have a high degree of confidence that the data will get there because the data is sent and there is an acknowledgement, and if the acknowledgement does not come back, then the data is resent. So unless a wire is broken for a long period of time, the data does eventually all get there. And so the data is, it establishes a handshake, makes a connection, sends the data. The segments come in with order numbers in them, so they can be reordered. So you can do something like send a file that is a group of many packets that are reassembled at the other end and create the intact file. The session layer is where you keep track of things like whether you have been authorized to get into a file share. So even if you can get to the right device with IP and get to the right port number with TCP, you still may have had to put in a name and password or something to verify that you are authorized to get it, and that's the sort of thing handled at the session layer. The presentation layer converts data from unreadable machine-oriented data into a form that humans can understand, like turning bits into ASCII characters or images, decrypting or decompressing it. And then you have the application layer where we all live most of the time, where you look at things you can understand, images, sounds you can understand, and so on. Things like web browsers and email clients are up here. So let's try a Kahoot. 4A. Favorites is good. There we go. 4A right up here. All right. All right. I'll give it another few seconds. All right. So, what kind of transmission goes through Ethernet? All right. Well, I guess I don't want to skip it. I'll let it go. Since these are broadcasting to your machines, I should lower the time. That time is high from last semester or something. Anyway, that's baseband that goes through Ethernet. Let me check my settings. Yeah, it is showing. All right, good. Showing answers on there. Wonder if I can change the time. Nope, won't let me do that from here. That would be nice. All right. All right. Where do you find the MAC addresses? Yep. I can't change the time now, but I'll try and change it for the future ones. We got somebody that's not answering, and it's making everything wait a whole minute. All right, that's at layer 2, MAC addresses. All right. And where are the hubs? tempted to hit that skip button, but I think it would cancel the scores. All right, layer 1 and the last one. Where do you find network file shares? All right. At 4 or perhaps 5. 5 is probably the best answer. All right. All right. I don't know if my grader knows who Haminsky is, or Pal. My grader might be able to figure out who you are from that information, and maybe not. All right. So, the TCP IP model is actually more or less closer to the way real hardware is written. That's why I wrote that, not just because of the limitation of Kahoot, but really only the first 4 layers are actually separated. They have different hardware devices and different meaning, and all the upper level layers are all just combined into the application. Typically your web browser just handles all of that. Although perhaps not the session layer, but anyway, the TCP IP model is more close to what hardware is. You have the bottom 2 layers connected together. This is your NIC and the wires. Then the internet is the routers, and the TCP up here is the different processes listening on your machine, so it's handled by software. And then all these are pretty... the separation of these is more theoretical than real. In reality, you have an application that just has all them mixed together. So that's the game. These 2 layers are combined into network access. Then the internet layer is where the routers are, and that's real. Everybody understands that. And TCP and UDP are real. They're not a special piece of hardware, but they're certainly important to control your listening ports. So that's layer 4. And everything above that is called the application in the TCP IP model. Yeah. All right. And these all work by encapsulation. The bottom 4 layers do. So if you, at layer 4, you have a segment, and that's got the TCP port number, and that's like putting a letter in an envelope. That's included in a larger object called a packet that has an IP address, and that's included in a larger object called a frame that has a MAC address, and that's sent over the wire as bits. So they call it encapsulation, where you have the actual data you want is encapsulated in a segment, and that's encapsulated in a packet, and that's encapsulated in a frame. So it's like opening several envelopes to get at the actual data inside. So you can remember the segment terms this way. You have segment at layer 4, packet, frame, and bits at layer 1. So you can think of the sunblock SPF 10, if you like, as a mnemonic for that. So when you receive data, it comes in as a bunch of bits, and now you have to decapsulate it, stripping off all those addresses to pass just the useful data up to the application layer. So that's what happens. The bits are converted to frames. Frames are converted to packets by removing the MAC address. The packets are converted to segments by removing the IP address. And the segments are converted to application data, removing the TCP port number. And then your application gets the data it wants. All the addressing information is gone, just like opening an envelope and throwing away the envelope and keeping the letter inside. All right, so MAC addresses, media access control addresses, They are assigned to a network adapter when it's manufactured, and everyone is supposed to get a different unique MAC address, 48 bits long. The first 24 bits are assigned to that organization, like Intel or somebody that makes the NIC, and then the remaining 24 bits are used to specify the individual NIC. In IP version 6, they use these things called EUI64 addresses, but that's at layer 3, and they do include sometimes the 48 bits from the MAC address, which is a privacy issue. But anyway, the MAC address remains 48 bits long for Ethernet. IP version 4 is what most traffic is still going over. Maybe 80 to 90% of the current web traffic is still using the older IP version 4 system with these 32-bit addresses that look like that, 192.168.0.1. It's 32 binary bits, and they prefer to write it as 4 decimal numbers, each 8 bits. And so the header has a whole bunch of more to it besides the addresses. It's got time to live and a checksum and some padding and such. But the main thing you think about here is the source address and destination address, each of which are 32 bits long. Now, in principle, this is a feature of IP version 4 which turned out to be a bad idea, but when IP version 4 was first brought out, there was a competing layer 2 protocol called Token Ring. And Token Ring could move much larger frames, like 10 kilobytes. So you would have a possibility that data could enter a router and have a packet that was larger than it could be transmitted on the other side of the router. So it would have to break that packet up into a bunch of packets. And that's called fragmentation at layer 3. This turned out to be a security problem and a performance problem and everything, and they got rid of it in IP version 6. Anyway, that's the game here. In IP version 6, they switched to path discovery, where you find the lowest packet size handled on a route and then resend the data with that size. Yes, they were warning we were running out of IP version 4 addresses, and we did run out of IP version 4 addresses. They're essentially all gone now, and pretty much all new deployments have to use IP version 6, or they have to purchase used IP4 addresses from people that are hard to get. So modern deployments are moving to IP version 6, which is pretty much the same thing. The only major difference is the addresses are much longer. A few of the goofier features have been removed, like IP fragmentation, but the main thing is you have a source and destination address, and it's 4 times longer. So we won't run out of them, and these are these addresses that look really long. Like this is an IP version 6 address, FE80::AEBC, all this junk. It is 8 fields, and each field has 4 characters, and it's hexadecimal, so each one of these is 16 bits. So the whole thing is 128 bits, 4 times longer than IP version 4, so we will never run out of these anytime that any of us need to worry about. All right. So IP version 6 is kind of a problem. A lot of people are sending data over IP version 6, but a lot of security devices have not yet upgraded to handle it. So there are people who can sometimes get away with violating security rules, like running BitTorrent over IP version 6. So what some people do is they disable IP version 6. You can go in your network properties on Windows and turn it off if you're not using it, to stop people from using it for nefarious purposes. All right. Now, when the original internet was started long ago, the idea was the first number would tell you what company you were at, and all the rest were for specific devices, and you could only go up to about 100 total companies. And that originally they thought that would be okay because there were only 4 universities on the internet, and they didn't think it would ever grow very big. But it, of course, did grow big. So until 1993, they used classful addressing, where the first half of the addresses were Class A, and half of what's left was Class B, and half of what's left was Class C. And there's Class D and E that don't really matter much. But the point is, this is large networks that can have up to 16 million devices on the same network, and only the real original gangsters of the internet got those, like IBM and MIT. And Class B is what City College got one of. These are the medium-sized addresses that have 65,000 possible addresses in their network. And the Class C is by far the most common. You can only have 254 devices on your network without using network address translation. Anyway, that's classful addressing. This was used until 1993 because it's possible to have up to 2 million unique companies on the internet this way, but even that's not enough. So after 1993, they extended it to classless interdomain routing, where you can have any network size. So you put this slash number here. A /8 means the first 8 bits determine the company, and the remaining bits determine the individual device. 16 is Class B, and 24 is Class C, and you can now have other sizes like /20. This is what City College used for its wireless network a while ago. It would take the 147, 144, and it would take 16 of these Class Cs and combine them into one big network, so you can have up to 2,000 students on the wireless network at once with these addresses. And you can make the network any size you want with any of these slash numbers. All right. There are certain addresses reserved for private addresses, so you can use network address translation. See, there you go. Yep, a static Class A address. Yep, the old days, yeah. So RFC 1918 defines certain ranges for private use, like the Class A starting with 10, and the Class Bs from 172.16 to 172.31, and the Class Cs starting with 192.168. So you can use any of these as your private addresses, and if you send packets onto the global internet with a destination address like that, it will just be thrown away because they're not used, not assigned to any particular company. They're intended for local addresses. All right, let's take a look at the 4B, and before we do it, I'm going to adjust the timing so that doesn't happen to us again. If I can figure out how. Well, edit. That's how. Okay. Might be move over here in case it shows the questions. If I edit it, where is the timing? Settings. I'm finding it. Okay. No, there's no time adjustment. Oh, I think I remember this garbage. I think I have to adjust the timing. Yes, slide by slide. Very annoying. All right. Still won't take too long now that I've found it. I changed it in a previous semester because of the delay in the streaming, and it wasn't until this semester that somebody showed me how to project it directly to your screens, so we don't have to do that. All right, so this is 125 for A, which this thing has hidden from me. All right. There. 4B is what we want. All right. All right. All right, I think we got everybody. All right, so where do you find segments? All right, they're at layer 4, TCP segments. All right, where are the 32-bit addresses? All right, that's IP version 4. All right, so what class is that address in? That's Class C. The higher numbers are in Class C, up to 223. Yes, that is Umbrella's IP address. A good one to have memorized. You can use it as your DNS resolver. All right. And where do you find the 48-bit addresses? All right, those are the MAC addresses. All right. All right. I might have seen that before. That's a real name. And I think I've seen that before, but we never did figure out who that is. So quite a few people are answering and likely not to get points, which is fine as long as you don't care. Anyway, so let's go on here. So, network address translation, I mentioned. This is how you deal with the fact that they run out of IP version 4 addresses and how you share one address among many devices to save money. So you typically combine it with port address translation. So you can have many devices sharing one IP address, and the traffic is separated by the port number on that IP address. There are some old techniques called static NAT and pool NAT, which I've never seen used in the real world. Port address translation is the one that's really popular, where you have one device up here serves as the router with a real public internet address like 147.144, and that you have to pay for. And then this device could go through a hub, or more commonly these days you'd buy a router that combines all the devices in one box, and then it hands out local addresses like 192.168 to all these devices, and they all go out on this public address with different port numbers. Address resolution protocol is used to find things. The problem is layer 2 has hard-coded addresses in all the network cards, and those are random. There is no order, and so you have to find the router. And so you find it by asking with a broadcast packet, who has 192.168.2.140, tell me. And somebody will reply and say, this MAC address has that IP address, and now you can find something on the network. And the most common thing you want to find is the router to get off to the internet. There's also reverse address resolution protocol, which was a competitor to DHCP, and you don't see it much anymore, that will let you get an IP address to put on your device that doesn't have one. So if you want to find your way to the internet, first you send an ARP request, you get an ARP reply. Now you know the MAC address of the gateway, you can now send your data to the internet. And the problem, of course, is you can do ARP poisoning. None of this traffic was designed in the old days of the internet when nobody thought about security, so there isn't any password or encryption or authentication anywhere. So an evil attacker can just send false ARP replies claiming to be the gateway, and now all the devices in that coffee house or whatever network you're using will believe that this is the gateway and send all their traffic there. This device can forward that traffic, and now you have become the man in the middle. You can now read traffic as it goes by and modify it if it's not encrypted, which is one of the many reasons why everybody should be using HTTPS for everything. And it's also something which you could solve by running a VPN on your laptop or your phone, so that even if somebody is in the middle, they won't be able to read or alter the traffic because they won't have the encryption key. All right. So unicast traffic is what almost everything is. Well, isn't there any focus on security? Well, because people believe that there weren't very many hackers. This is what Microsoft's official position was until 2002. There aren't very many hackers. They don't really do that much harm, and it's a waste of time to try to design things that can't be broken into with malicious attacks. Most of our customers are just trying to do their job. You only want to make stuff good enough that an honest worker trying to get their job, do their job, can succeed and get the bugs out that cause it to crash, but it's just expensive and a waste of time to try to stop all the deliberately malicious attacks. That was the official position until 2002. So hackers had kind of a wide open field with no defenses to overcome for a while, until the hacks got so bad that Microsoft had to reverse course. And all the other companies had to basically make the same decision, that you really do have to spend your time and money writing more secure stuff, even though that's more expensive, because otherwise it will get hacked, and you can't put up with that anymore. Yeah. The original idea was you didn't really think about the internet much. You mostly thought about a local area network, and you figured that most of the action is in my room anyway. It's my employees printing things on the printer, so I don't really need to worry about attackers because everybody in this room is my employees, and you can trust everyone inside the trusted perimeter. These ideas made sense when the internet was not used that much, and when it was an earlier, more innocent age. Anyway, so most common traffic is one sender to one receiver. Yep, that's right. Then you get Zone Alarm and McAfee and all the stuff after that, Cisco Umbrella and everything. So multicast is in principle available, where one sender would go to several receivers, but it turns out to only be used by routing protocols, which is kind of amazing. So if you have a popular movie on Netflix and there's 1 million people watching that movie, there really are 1 million separate one-to-one streams delivering that movie to each person, which is spectacularly inefficient compared to, say, broadcast TV, where you send out one signal and it reaches all those millions of people from one signal. But it turns out to be the way it's really being done. So you can send broadcast traffic. If you send it on layer 2 or on layer 3 to this IP address, all ones, and that sends it to the layer 2 broadcast, which is the MAC address that's all ones, and that will just send to every device you can reach, everything up to the router, everything on your layer 2 network. And this is what you do when you're looking for an IP address with DHCP, or when you're sending an ARP request. There used to be something called a directed broadcast, where you could give the network part of an address and fill the rest of it with ones, and this would then travel over the internet and reach every device at the far end. And this turned out to be too dangerous. It was used to stop the reverse packet multiplication denial of service attacks, called them Smurf attacks, where you would send pings to a whole network, and all those thousands of replies would go to your target. So this was blocked long ago, and these directed broadcasts are no longer forwarded on the internet. But the direct broadcast to your local area network is essential. All right, and there's also an issue of promiscuity. A network card typically the first thing it will check when it receives a packet is whether the MAC address is matching the MAC address on the card. And if it doesn't match, it will just ignore it and not send it up to layer 3 or layer 4 where it's used. So your network card will politely ignore all traffic that's not addressed to it. And that's because you might be using a wireless network or a hub network which cannot direct traffic to your device. You're actually going to get packets that are frames that are aimed at someone else, and you have to ignore them. But you can turn that off, and that's running unique and promiscuous mode, where it will actually pass every frame it receives up to higher levels, even if it was not aimed at you. There is no normal reason to do this. The only reason you do it is because you're an attacker trying to read somebody else's traffic, or you're trying to debug a problem or something. So entering promiscuous mode requires root privileges, and Microsoft even has various protocols available to detect if one of the NICs is in promiscuous mode, because they regard that as a suspicious activity that should raise an alert for the administrator, which is pretty reasonable. So TCP at layer 4 has got source port and destination port, and then sequence and acknowledgement numbers that are used to reorder the segments that come in And then these flags are the other important things to us, things like SYN and ACK. It has other things here that don't matter that much to us right now. So the TCP ports, the low-numbered ports, are called well-known. They are reserved for really important services like HTTP and TFTP and SNMP and such, and so you can only listen on them with root privileges. All the rest are used for temporary, less important things like games and chat clients and stuff. So a socket is a combination of 4 ports. You have a local address and your local port number, and you connect to the remote address. This is SSH, listening on port 22 on some server. So these 4 numbers together form what's called a TCP socket. You can now send packets from the client to the server, and they will be sorted out at both ends. So you have, it's as if you had your own wire to send data and receive data from the server. It's going over a shared network and going into a shared server, but it's been addressed correctly so that the traffic is sorted, and these 2 devices now have two-way communication on this socket. Now the socket has a state. Listening means it is waiting for a SYN. Your server is ready to receive a connection, but it hasn't got one yet. Established means it's got a complete handshake. And you establish this socket with SYN, SYNACK, ACK, the 3-way handshake. All right. So SYN is beginning to synchronize with the server. Acknowledgement is used to acknowledge packets. So you send a SYN, the server sends the SYNACK, you send an ACK, and now you have an established connection until you end it with either a reset or a FIN or a timeout from not using it for a while. All right. And so there's the handshake, SYN, SYNACK, ACK, to make a connection over TCP. This is like calling up somebody on the phone. You say hello, and they say hello, and you don't start talking until that happens. So actually you ring the phone, they pick it up, you say hello, they say hello, then you send the message. That's how TCP works. You don't bother sending data to someone that's not listening. First you make sure they're ready to receive the data. All right, UDP doesn't do any of that. UDP is like broadcast television. You just spew out data, and you don't even know or care whether it gets there, whether the person's listening. You're just continuously sending out data. It's used for things like security cameras. They're just spewing out data. And all it has is it has ports, but it doesn't have any SYN or SYNACK or reset or anything. There is no connection. It just transmits data, and if some of the packets get lost, you never know or care. You just keep sending it because you're something like a security camera sending a live feed. All right. That's right. The UDP joke in the chat is right. All right, so 4C. And I'm going to have to first go over here and adjust the timing, which worked last time. So, okay, it's edit. Okay. And there we go. Right. And just save it somehow. There's the save button. All right. All right. It's 4C. Oh, it was there. All right. Anyway, it'll be there in a minute. There. right. We lost somebody. I'll wait a few seconds to see if they come back. Aha. All right. Well, now we've got everybody. All right. So what kind of transmission? Wait, have we done this one? Wait a minute. Haven't we done this one? Wait a minute. All right. I'm going to take a look. This is the wrong one. I think we should be doing 4D or something. Let me take a look at my slides. 4C. Maybe I hit the wrong one. Yeah, all right. Favorites. 4C is here. And it shouldn't be that slow either. Let's see what we've got here. Well, I didn't think of that, Beach, but I'm not going to deliberately repeat one. All right, we had 11 people. Well, maybe, there we go. I got 11. All right, let's see if this looks like the right one. Oh, all right. I'll wait a couple seconds, see if we got any more. All right, this should be better questions and not so slow. Let's see what the deal is. All right. All right. Okay. What's the transmission that uses 255, 255, 255, 255? All right, that's broadcast. Good. All right, and what ports require admin privileges? Yep, the low-numbered ones, up to 1023. All right, so what TCP flag initiates a connection? All right, that's a SYN. Good. All right, and what UDP flag initiates a connection? Yep. Didn't fool anybody much around here. Yeah, that's right. There is no flags, no connection in UDP. None of that. You just send the data out. All right. All right. And Forte goes one twice. And that's all right. All the rest are first-time winners. All right. So we stop the recording.